Okay, so we're going to continue to look at this first law of thermodynamics, and we're going to focus on two properties, heat and work. Now, the first law of thermodynamics says that the energy of the universe is assumed to be constant, not changing, not getting more, not getting less. But we can undergo changes within the amount of energy in a system, and we're going to be looking at that in this section. Okay, so let's kind of introduce this concept. So, even in my little hands, it's not possible to determine the total amount of energy between my hands. It is certainly not possible to know the total amount of energy in the entire universe. Okay, so we can't know that. And as I discussed about, looking at just the gases in my hands, there's a certain amount of gas. They're moving, the electrons are moving, the nucleus is held in check from the nuclear energy. Not only are the molecules moving like this, but they might be tumbling. Each one of those are separate energies associated with those motions. There is energy stored within the bonds of those gas molecules in there. Those bonds are wiggling, and there's energy associated with those wiggling. There's just way too many things going on to know the amount of energy in the universe. But we can determine changes in energy. So if I had a gas in my hand and I put some hot air in there with them and made those molecules move faster, okay? Or I could compress them or expand that gas. It could undergo a change, and then I could determine the change in internal energy by doing that. Now we know that because it's a state function that it could be final minus initial, but we don't know those guys. We don't know the final, we don't know the initial. But we do know this. Whatever that gas is doing, okay, and whatever change in energy it associates with it, because of the first law of thermodynamics, if the amount of energy in that increased, then the amount of energy outside of that would have to decrease, okay, vice versa. If the amount of energy in here decreased, it had to be resulting from the energy surrounding that increasing. So SYS stands for system. That is the thing that you're studying. SURR stands for surroundings, and that is everything else in the universe. So whatever the system is doing, the surroundings is doing exactly the same thing, but notice the sign there, opposite in sign. So if one is increasing by 5 joules, the other one is decreasing by 5 joules. If one is decreasing by 55 joules, the other one is increasing by 55 joules. Whatever the one is doing, the other one is doing exactly the same magnitude, but opposites in signs. So what we need to do is focus on the delta E. We cannot know just the E, how much energy is in any system, but we can look at and explain and talk about changes in energy of a system. And we have to think about how in the world can you obtain values for the change in energy. All right, there's only 2 ways that energy can enter or leave a system. Only 2 ways. And so if something is going to gain energy or lose energy, it's going to happen by these 2 processes. One is the transfer of thermal energy. Now, the definition of the transfer of thermal energy is heat. A lot of times we say heat transfer, but that is redundant. Heat means transfer of thermal energy, and that transfer always goes from something that's higher in energy, higher temperature, to something that's lower temperature. And it's a transfer of thermal energy. That's a movement of those molecules. It's a kinetic energy transfer. So if over here the molecules are moving very fast and they bump into this system that we're moving slower, they're going to transfer that thermal energy. Those molecules are going to move faster, and that's what we call heat. All right? The second way that energy can get in or out of a system is by way of work. Now, work is the application of a force through a distance. So when you push an object and you're pushing force behind it and it's moving across a certain distance, that is work. A gas, when it expands, it's pushing out against the surroundings. If a gas is being compressed, the surroundings is pushing in on it and it's getting smaller. So a distance is being traveled with a certain force. So that is the 2 ways that energy can get in and out of a system. Well, if that is the way it can be transferred, and if the amount of energy in the universe is not changing, if a system is changing how much energy it has, and the only 2 ways to do it is by heat and work, then in a roundabout way, mathematically, the first law of thermodynamics looks like that equation that you see right there on the screen. The change in energy is equal to, well, I have two symbols here, Q and W, so let's define those. This is an equation that you need to know, so I've got a blue box around it. The Q stands for heat, okay? So that's the symbol that we use for heat. Notice it's a lowercase q. It's not a capital Q. The process that it undergoes is dependent upon the amount of heat, the amount of thermal energy transferred is dependent upon the process, as well as the W. It's easy to know what W stands for. It's work, okay? So the only way a system can undergo a change is through Q and through W taking place. All right, already mentioned that. Now, it might be helpful for you in order to hold on to this notion, or maybe your curious mind is saying, how in the world can heat and work not be a state function, and yet the change in energy and that internal energy is a state function? There is an explanation of this process for you in your book, and you could read through it. It is not something I'm going to test you over, but for some of you, you might be really curious about that, and you might want to read about how in the world the Q and the W can be path dependent and the change in energy is not. Okay, so there's a sign convention that we have to get really used to, and I see students really struggle with getting a handle on this and holding on to it. But let's try to, first of all, think about energy increasing and decreasing. Look at the bottom, okay? The delta E equals Q plus W. If a system, and let's just think of a system as the gas in my hands, if it is going to increase in energy, okay, there has to be two things happening. There could be two things happening. I could put thermal energy into there, okay? I'm putting it in, it's taking it in, it's absorbing that energy, and that would make it increase. Or the surroundings could do work on it, okay? Push on it, and that would put energy into it. Or the opposite could happen, okay? Thermal energy could leave my hands, okay? Or my hands could expand, or the gas in my hands could expand, push out on the surroundings, and those two things take energy out of. Because if the system is doing the work, he has less energy in it, okay? So thinking about that, let's look at the sign convention that we see here on the screen, starting with heat. Heat is negative if a system is getting rid of its energy, okay? So the system is losing thermal energy. Think about it. If it's negative, delta E is going to get smaller. It's decreasing its energy if that Q is a negative number. So negative heat means the system is giving its heat to the surroundings. If it's a positive Q value, that means the system is gaining thermal energy from the surroundings, okay? Now work. Work is negative when the system is doing work on the surroundings, okay, by the system onto the surroundings. So the system is doing work, it's expanding, it's pushing out, and it's losing some of its internal energy, and therefore it's a negative sign. Work is positive if the surroundings is doing work on the system, pushing in on the system. So that's the sign convention. Okay, so we have two equations there. We have talked about those two equations, but just briefly mention them again. Delta E equals Q plus W tells me that the only way I can change energy of a system is to put heat in or do work on it, or vice versa, take heat out, have it do work on the surroundings. Sometimes it's difficult to monitor what's happening in the system because it's closed off and I can't get in there, but I can monitor the surroundings. So if I know what's happening to the surroundings, I can then make a statement about what the system is doing, because they have to be equal in sign, equal in value, but opposite in sign. So with that, I've got some questions for you to consider, all right? I want you to look at this question here in just a minute. I want you to stop and choose an answer for it, okay? So I want you to look at that. We have, in terms of heat or work, it might not be talking about both, and it's not actually. It's either talking about a heat or it's talking about work, and it's either talking about gaining a positive value or a negative value for that. And I want you to think, what's the sign and which are they talking about? So here's the statement. Sweat evaporates on the skin, cooling the body. That's why we sweat. It evaporates and it cools the body. Now I want you to think about the sweat itself as the system. And if you're thinking about sweat as the system, stop and think about it and choose one of those. Okay, well, did you know that it was talking about heat? Okay, if the body is cooling down, that's a heat association with it. It cools down because it's giving some of its thermal energy to the sweat. So the sweat is gaining that thermal energy in that allows it to evaporate. So if it's bringing it in, the sign convention is positive. All right, let's have another statement here. In this one, I've got a gas in a cylinder. This happens in your car engine, okay? And it's expanding for some reason, okay? Which we're not going to get into with our car engine, but we see this picture. The gas in that car cylinder expands, and it's pushing the piston up. I want you to stop and think about which one of those statements am I describing? Am I describing about heat or work, and is it a positive or is it negative? All right, hopefully you chose one. And if you chose that it's talking about work, it is pushing a force against across a distance, okay? The piston is moving, that's work. And the system is pushing up against that surroundings. So it is the system doing work on the surroundings, and that is a negative sign for that. So you've got to be able to recognize work when you see it, you've got to recognize heat when you see it, and you need to know the sign convention of those two things. Okay, so now that we know Q and W, we're ready to put them together and see if we can calculate a delta E for this process. Now, what I want to have you do, and I'll kind of introduce it here, get you started on it, we're going to calculate delta E for this process. So we know that delta E is equal to Q plus W. So you're going to read through that and see if you can find the Q, the W, think about the signs of those, and determine a value of delta E. Now we want your value for delta E to be in the units of kilojoules here, so make sure you're watching out for that. Now pause the video, think about it, and come up with an answer and then resume. Okay, hopefully you walked through that one and came up with an answer, and maybe your answer was C. If so, you're correct. If you feel real comfortable with choosing C and why you choose C and you feel great about that, you can stop right now. But if you have any kind of shakiness, you didn't pick C, or you're wondering how in the world that came about, then watch on and I'll show you how the answer is C. First of all, let's think about the Q. All right, so we'll begin with the Q. That's the heat. And it tells me that in this process, 25.5 kilojoules of heat is being released to the surroundings. So it's already in kilojoules, that's nice, and it's 25.5, but if it's being released, it's exothermic. So it is a negative value. Hearing that word released, now what they won't say in a problem is it released a negative 25.5 kilojoules. We don't say it that way. The word released is telling me that the thermal energy transfer gives me a negative heat sign, and so that's how it is. It's kind of like if I were to say I lost 5 pounds, I wouldn't say I lost a negative 5 pounds. Now my change in mass is negative. If I did final minus an initial, that would be negative, but you don't throw that negative sign in there. This is a kind of a subtle thing when we're talking about changes, but with heat, if they say that it is being released, it has to be a negative number. So then we have our work information. Now, it tells me it's 500 joules. Now, 500 joules is 0.5 kilojoules. Okay, so we could do the conversion process to get that there, but let's think about the sign. Okay, the system is doing work on the surroundings, so it's pushing out against that. It's doing work on the surroundings, so that one is also a negative. So when I add those two things together, that's why I get a 26.0. And sig figs, you keep the last number of places to the right of the, or the least number of places to the right of the decimal point, so that is 26.0 as our value. Okay, so if I know heat, if I know work, I can get the change in internal energy. This is of a system doing work on the surroundings and exchanging heat with the surroundings. Then that ends part 2 of our thermochemistry discussion.